All right, let's dive into this explainer and completely rethink everything you thought you knew about our cosmic neighborhood. When we look up at the night sky, it's really easy to feel this sense of profound peace. We've basically been taught since grade school that our solar system is a steady, reliable place. But as you'll see, modern science has a completely different story to tell. We naturally assume the planets just move in this perfect, predictable clockwork. After all, the sun rises, the sun sets, and the planets predictably glide across the sky. But what if I told you our solar system's history is actually a chaotic melting pot? What if I told you that the very ground you're standing on right now only exists because of an ancient, incredibly violent cosmic pinball game?
Here is our roadmap for today's explainer. First, we'll meet our cosmic neighborhood, then look at the heart of the system, explore the illusion of order, dive into the great planetary migration, and finally, head out to the edge and beyond.
Okay, Section 1, meet our cosmic neighborhood. Meet the planets. Let's start by just grounding ourselves in the current, familiar structure of our planetary system. Because before we can appreciate the chaos of the past, we really need to understand the apparent order of the present. So we've got a stark contrast right off the bat between the two main zones of our solar system. On the top, we have the four small, solid terrestrial planets hanging out near the Sun: Mercury, Venus, Earth, and Mars. These guys have compact, rocky surfaces. But cross the asteroid belt, and you enter a completely different realm, the massive, swirling gas and ice giants. Jupiter, Saturn, Uranus, and Neptune are entirely different beasts, made mostly of hydrogen, helium, and freezing ices.
Moving on to Section 2, the heart of the system, our star. Now, we absolutely cannot understand the system without looking at the engine that drives it all, the anchor holding all these planets in their lanes. And that engine is an absolute behemoth. 99.8%. That is how much of the entire solar system's mass is packed into the sun. Think about that for a second. Every planet, moon, asteroid, and comet you have ever heard of makes up literally just that tiny remaining 0.2%. The gravitational dominance of the sun is the absolute law around here. But the sun isn't just a solid ball of fire, right? It's this incredibly complex, layered plasma engine. Energy is generated way down deep in the core, where the temperature hits an incomprehensible 15 million Kelvin. This is where thermonuclear fusion happens. Protons are literally slamming together to release massive amounts of energy. That energy then slowly bubbles up over hundreds of thousands of years through the radiative and convective layers, finally reaching the photosphere. At a much cooler 6,000 Kelvin, that photosphere is the bright, visible surface we actually see shining down on us here on Earth.
Which brings us to Section 3, an illusion of order. A static system? Now, up to this point, everything sounds incredibly stable. The sun holds the center, the rocky planets stay close, and the gas giants circle far away. But as we look past the sun and really dig into the data, we hit a massive scientific paradigm shift.
For centuries, thanks to Isaac Newton's brilliant formulation of the laws of gravitation, scientists viewed the orbits of planets and asteroids as perfectly predictable and static. The Newtonian universe was deterministic. The assumption was pretty straightforward. Where the planets are today is exactly where they were born 4.5 billion years ago. They formed from a disk of dust, condensed into spheres, and just kept spinning in place like a well-made clock.
Under that classic theory, we used to think the asteroid belt, that ring of rocks between Mars and Jupiter, was just as neat, orderly leftover. It perfectly preserved a thermal gradient from the time the solar system formed. Hot, melted rocks stayed close to the sun, cold, icy rocks stayed further out. Tidy, right? Well, over the last few decades, modern discoveries and supercomputer modeling have completely shattered that idea. The modern theory reveals a dramatically scrambled reality. It's a highly dynamic system sculpted by great change, immense movement, and chaotic mixing.
And that takes us to Section 4, the Great Planetary Migration, the Great Shakeup. This is the thrilling twist in our story, the era of chaos that completely restructured our solar system.
This era is defined by a wild concept called planetary migration. Modern models show that the giant planets didn't just quietly stay put where they formed. Instead, they migrated over massive distances. I want you to imagine Jupiter and Saturn acting as these unstoppable gravitational bulldozers, changing their orbits and violently shaking up asteroids and icy bodies that had formed throughout the solar system. It was exactly like shaking up the flakes in a giant cosmic snow globe.
So how did this extreme movement unfold? It's explained by two leading scientific theories called the Nice and Grand Tack models. First, Jupiter, the heavyweight champion of the planets, plowed inward toward the Sun, coming roughly as close as Mars is today, which effectively emptied out the original asteroid belt. But then Saturn interacted with Jupiter gravitationally, pulling it back and causing a massive course reversal. As those two giants retreated, Uranus and Neptune were violently pushed outward into a dense disk of primordial icy debris. This gravitational pinball slingshotted countless comets and icy bodies all over the place.
And the definitive proof of this chaotic history? It's actually recorded right there in the compositional mapping of the main asteroid belt. If the planets had just stayed where they were born, the asteroid belt would be perfectly color-coded by temperature. But it's really, really not.
Instead of those neat groupings, observational surveys mapping the compositions of tens of thousands of asteroids show a wild smorgasbord. We see rogue, bluish, icy asteroids that formed way out in the freezing depths of space, sitting right next to reddish, melted rocky ones that formed close to the blazing sun. It's a total melting pot. This proves beyond a shadow of a doubt that materials from the extreme inner and extreme outer system were violently scrambled together by migrating giant planets.
And here's the crazy part. The mixing hasn't entirely stopped. While the massive planetary migrations ended billions of years ago, the asteroid belt is still highly dynamic today. Constant collisions are always grinding bodies down to smaller sizes. Plus, there is this fascinating phenomenon called the Yarkowski effect. Basically, uneven daily heating and cooling from the sun acts like a tiny slow-motion thruster on small asteroids, slowly altering their orbits over millions of years.
Finally, let's hit Section 5, the edge and beyond. Far reaches. Let's zoom way out from the asteroid belt to the darkest, freezing edges of our cosmic neighborhood to see where the rest of that scattered debris ended up.
When Neptune was forced into its outward migration, it acted like a cosmic snowplow. It bulldozed a massive amount of icy remnants into what we now call the Kuiper Belt. That's a donut-shaped region that is home to dwarf planets like Pluto. But Jupiter's immense gravity was far more violent. It slingshotted countless other icy bodies completely out of the planetary plane, forming the vast, distant, spherical Oort cloud, which is up to 100,000 times further from the Sun than Earth is. This distant cloud is actually the mysterious home of the long-period comets that occasionally light up our night sky today. So why does understanding all of this matter so deeply? Well, 4,000 plus. That is the number of other solar systems, exoplanetary systems, astronomers have now discovered in our Milky Way galaxy. For a long time, we couldn't figure out why these distant systems looked so weird. Like, why did they have giant gas planets orbiting incredibly close to their stars or on highly elliptical paths?
But by decoding the violent, chaotic melting pots that somehow resulted in our stable Earth, we gain the cosmic blueprint. Understanding our own history of migrating planets and scattered debris is the ultimate key to understanding how planetary systems are built and evolve all across the universe. We aren't an isolated, boring clockwork system at all. We are a surviving product of extreme dynamic change.
So as you look up at the night sky tonight, we have to ask a profound question. If our supposedly predictable solar system is actually a survivor of pure cosmic chaos, what incredible secrets, what unbelievable histories are hiding out there in the thousands of other solar systems in the dark? Keep looking up, keep asking questions, and I'll catch you in the next explainer.